It is 1 minute past 11, so let's get started. Hello to you all and welcome to eDrone seminar. Today our guest is Mateusz Pieniak from Evidence Prime. Mateusz graduated in computer science 4 years ago in 2017. During his studies, he worked on various topics in what is now called AI or machine learning or data science in these topics. He worked on face recognition, on speaker verification. He also worked in several companies getting experience in various fields of applied machine learning. And currently Mateusz is a Senior Applied NLP Scientist at Evidence Prime. I hope Mateusz will tell us a bit more what Evidence Prime does, but I will tell you it's a company which works at a very interesting intersection of healthcare and natural language processing. And today's seminar's topic is imbalanced text classification. So Mateusz, floor is yours.
Okay, hello everybody. Can you see my screen?
Yes. Yes.
Okay, so as Szymon told you, that today's topic is imbalanced classification, and we will share the lessons that we learned during tackling the problem of screening automation for the evidence synthesis domain, especially for systematic reviews. So I work as a scientist, as Szymon said, and my job is to understand the world in a scientific way and apply that to products and try to improve them. So we are Evidence Prime, and we are a remote-first company with the main office located in Krakow, in Poland. And we are a spin-off from McMaster University, which is some sort of Silicon Valley of something called evidence-based medicine. We have 20 people on board with 8 software engineers who create products for different clients, and mostly for the public sector, which consists of WHO, European Commission, some government agencies, medical societies, and recently for some pharma industry. So before we dive into the details, I will need to briefly explain you what systematic review is. And in short, systematic review is some sort of aggregation of different studies with that are collected in unbiased way with one very specific goal. And that goal is that we don't want to skip any relevant studies. So in other words, we want to maximize the recall or sensitivity of our collection of studies. And there are different studies. So basically, the other goal for systematic reviews is that in the world, you will find different opinions of people. For example, if you have a virus infections, you can call your mom and she will tell you that you should take the garlic. And you can call your grandma and she will tell you that you should take honey. And you don't know what to do. So first thing you should do is to look for systematic review, how to get cured. And different type of studies can be included in the systematic review. So for example, these are case reports, which I call some sort of scientific news, because this is like a case of, for example, for a doctor that had a patient and he treated that patient with a specific drug and this patient was cured. But actually, we don't know whether it was this like spontaneous like remission or something. So this is like a very big scientific news. The other type of studies that you may find in systematic reviews are case control studies. And these refer to observational and retrospective studies. So for example, we have 2 subjects in a hospital with a cancer, and we try to look for the history, for example, whether they were smoking or not. So most you can do, as far as I understand, is like some correlation analysis, because it's very hard to prove the causation of the outcome. And the next type of studies is cohort study, which is as well observational, but this time prospective. So for example, you know that people are smoking and you just look into the future and wait whether they get cancer or not. And you can say that on top of that study, you have randomized control studies. but it's a bit misleading because different studies have different purpose. For example, because randomized control studies work that way, that you have a group of people and you randomize them into some groups. And if you heard about placebo effect, you most likely refer to randomized control studies when you compare, for example, one drug with another drug. But sometimes we cannot force people to do something. That's why, for example, for smoking, we cannot force people to smoke and do studies on them. That's why this care is not always like from bottom to top, because sometimes cohort studies may be beneficial as well to include in systematic reviews. So, and it's worth mentioning that there are other types of these data aggregations. For example, scoping reviews or evidence maps or rapid reviews, but their purpose is slightly different. They don't try to aim, they don't aim to maximize recall, they just want to be done fast or see what's on the market, like in the market of scientific literature. So now we need to understand how the process looks like. So first of all, we need to define what we are looking for. And then we need to look for evidences and write what we want into some search engines for different databases. And one of the requirements for systematic review is that we need to look in different databases. Like one database is not enough to have a comprehensive search. These search engines mostly support the Boolean logic. So you just write like very big Boolean expression that that can be for like a few pages of words, for example. And then since we have multiple databases, we need to remove duplicates because the same study might exist in different databases. So we have a stage for duplication removal. And then we come in with selection of the studies. So this is the screening step that I mentioned at the beginning. And it consists of two sub-steps, especially for title and abstract screening and full text screening. We'll focus only on the titles and abstracts for the presentation. And then once we are done with screening, we need to extract data from these studies and analyze data. And the outcome of the systematic review is something called meta-analysis, which is usually displayed as a forest plot. And this is an example. So this refers to treating corticosteroids for treatment of COVID and trying to evaluate whether adding corticosteroids to a standard care, which is like being in a hospital, for example, is it beneficial for the outcome defined as all-cause mortality. So trying to see whether just treating people with corticosteroids in the hospital will allow them to survive longer. And indeed, you have different studies here as a rows in the table. From each study, there is some statistical test. So you have like a risk ratio, and you have some sort of bias estimate. And based on that, you can see on the bottom this kind of red triangle, not triangle like this, this red dot, this black dot, and it says that it's slightly beneficial for your purpose. So it helps us to answer the question. It's worth also mentioning that meta-analysis don't need to be always done for systematic reviews. It can be for any synthesis, but if it's done for the systematic review, then it's like very good. Yeah. So we understand what systematic review is and how the process looks like. So now is time to solve a problem. How to solve the screening problem. So first thing we do, we look for some benchmark, and in the benchmark usually have some data sets. So we found the data set called Cohen's dataset. So this data set contains of decisions about screening. And these are binary decisions, which means that should I include the study in the systematic review or I shouldn't? And our goal is to like classify examples or rank the examples with the goal to maximize recall. And you may find there are different metrics for that. For the imbalanced classification, like F1 is okay, or average precision, which is sort of like a area under the curve of precision recall curve. But these two metrics are like too generic for our purpose because they don't maximize the recall that we want. Of course, you can imagine different metrics, like perhaps you can optimize the precision, given the recall 95%, for example, that's okay as well. So this particular data set contains of 16 systematic reviews. And I'll repeat again, like a systematic review is basically like a set of studies. So for each systematic review, we have like decisions, binary decisions, ones and zeros. And so these are statistics for these for the data set. Imbalance ratio is not very low, but not also very high. It's around like 4%. And the setting for this benchmark was that 50% of the studies went for training with cross-validation, like cross-training, and 50% of studies went for testing. And then we just made prediction from each fold model and averaged all the predictions. So classical training settings. And then if you train the model, we need some relevant metric for our purpose. And we know that, they defined the metric called work state oversampling. And basically, this is like a trade-off between the recall that we are interested in and the work. So when it's high, basically the recall is very high, but the amount of work we need to do, like the real screening work, is very low. So work is defined as amount of like all positives that were returned by the model. And these are true positives or false positives relative to all of the studies in our review. And it's worth mentioning that it's not 0-1 metric. It's actually like from different ranges. So we also need to take that into account. So for one systematic review, like 60% is not as good as 80% because there's like different ranges for the minimum and maximum values. Also, for a dummy model, this metric is equals to 0, because then with dummy model predicting all ones, the recall will be 1. But if we're just labeling everything as 1, the work will be 1 as 0. So work state over like sampling will be 0. I will explain what this sampling means in a minute. But also there are like two things to notice. First of all, that it's sort of hackable. I mean that it very depends on the number of n. So if you have a lot of examples in our systematic reviews, like trashy examples, then we can like artificially make it like higher. Of course, as I said, we cannot compare this metric between data sets because it's 3%, but it depends on the number of examples. So for one data set, it's very hard to achieve good WSS, whereas for the other data set, it's very easy to achieve very good WSS. And this oversampling term in the metric basically measures the gains over like random order. What I mean that I will explain that on the next slide. So here we have on the y-axis, we have recall, and the x-axis, we have number of documents that we had to screen. And this random sampling, a random order, are like the dotted diagonal of this chart. So we can imagine that on average, if you have 100 examples and you have 10 positive examples in your data set. So if you distribute these positive examples random, like uniformly in your data set, then when you screen 10 examples, you will do like 10% of your work, but since it's uniformly distributed, you will catch like one positive example out of 10. So it will be 10% of a recall. So this is kind of like expected random order, because basically if you like try to shuffle that in a random order, you can get some negative values, but on average, it will be like around diagonal. So it gives us, so WSS gives us some sort of gain from that average of this random order, because basically if you do that work, it's like recall is equals to work plus WSS. So here recall is equals work plus WSS, which is like this red dashed line here. So this is what we are measuring, what we are interested in for the benchmark. So since we have a data set and since we have a metric defined for our purpose, it's time to train some models. So we trained 3 different models. So first of all, we tried classical CNNs over glove embeddings. For those who are not familiar, you can imagine that you have a list of words, and each word you can map to like a vector, and then you end up with a matrix. And then if you have a matrix, you can like treat this matrix as an image and apply it like some techniques from image recognition to to get some features out of that. Then we also tried LSTMs. LSTMs are it's like an architecture that spans over time. So you just look at words over time, but you have some kind of control unit inside that allows you to focus on the previous examples. So basically you have some skip connections inside that allows you to remember some information and use that information lately, but also to pass gradients backward. So we did that over ILMO embeddings, and we applied different regularization technique to that. So one regularization technique for LSTMs was variational dropout. I won't go into theoretical side of that, but from the practical side is that you don't have a dropout mask per time step. You have one dropout mask for each sample. That's the difference. The other regularization was recurrent drop connect, and drop connect is sort of generalization of dropout. And basically, instead of dropping the activation of the units, you can drop the weights in the matrix. So as the result, all of the neurons will receive the random, the input from the random subset of units instead of from the same subset of activations. And the last technique is embedding dropout, which is kind of very similar to what BERT does. It's like masking some words while you train. And also we tried BioBERT. BERT is like an architecture focused on self-attention for training the language model, but I think we don't have time to explain further. So we tried these models, and we tested that and compared with some benchmark called Swift Review, and it seems like our approaches are not so great. So Swift Review, like a benchmark, used very simple approach. They used TF-IDF compared with LDA, which is like latent dirichlet allocation, and they applied SVM on top. So they received very good scores. So we started wondering, did we do something wrong? And first of all, we tried to look into the papers, and this is like a paper called DocBERT. And basically, we learned that there exists some data sets, like Reuters, for example, that it's fairly easy data set. And the gain between like SVM trained with TF-IDF compared to some BERT-based, it's not so huge. So 86% for test F1 and 89% for the BERT-based, which is not a significant gain. But it depends on the data set. We also took to our data collection team to explain us the nature of this task. And they said that it's a very easy task because mostly they look for the keywords while they are doing screening. But the reason was slightly different, because when you have a recall and you want to maximize the recall, it really depends how many examples you have. So if you have 8 examples in your systematic reviews in this test set, it means that the resolution for your recall is like 12.5. So if your goal is to maximize the WSS for the recall equal to 95, then it means that you can either have recall equal to 100% or equal to 87.5, because your resolution is 12.8. And the reason was that in our experiments, we reported the one that was the closest, because 100 recall is closest to 95 than recall equal to 87.5. And it seems like the authors of the paper actually reported the one for 87.5, which is like the peak here, and it's like 0.7 something WS. So that's the difference. So we reproduced this paper, and it seems that now deep learning works in our case. Not like super great, but it works. Surprisingly, LSTMs over ELMO were a very good model. I'm not convinced about BioBERT because back then we were using the framework called Allen NLP, and I know that it was under active development. There might be some mistake. It was like over a year and a half ago, the results I'm showing. But yeah, this is the results that we achieved anyway. Okay, so these were like numeric results. Now I'll like share with you some of my recommendations for training the models. So first of all, we have imbalanced data set. We have a few included studies like a positive labels. So the question comes, can we use large models? So sometimes doesn't make sense because some data sets, as I showed you with Reuters, are very easy and don't require complex modeling. But there's like some misconception in the world that when you don't have enough data, you cannot train big models. So the thing is that you can, as we shown, but it matters how you train the model. So I refer to this paper from Jeremy Howard, this universal language model fine-tuning, UL and FIT, which basically shows that you can train big models, but you need to adapt some learning rate schedulers, so we need to do that wisely. So yeah, and also what's always not very obvious, that BERT is not always the best, better, because some models, as I shown you on this dog-BERT benchmark, is that LSTMs carefully trained and regularized can be also very competitive, and our results show that as well. Or it's with different tricks like knowledge distillation, which is sort of taking the knowledge from BERT and putting that knowledge into LSTM as a regularization technique. Also, there is a nice paper that I recommend to read that if you pre-train the language model with convolutional neural networks, it's as well very competitive to transformer architecture. And also a nice paper from Eric Wallace that BERT actually poorly understands the numbers. And I think the main reason for that is that it was a Schwartz piece, a tokenizer, and it like shatters all of the numbers. So this is the benchmark that I refer to, and that if you take a look at the numbers for the LSTM or knowledge distillation LSTM, it's still very competitive. But one thing worth mentioning is that the BERT's purpose was not to have very super high score, but actually the purpose was simplicity. So with BERT, you can achieve a lot of tasks very easily, while for like different architectures, you need to figure it out the architecture by yourself. Like, for example, if you want to have some question answering, you need some like old models like these SIM models, which is like, I don't like enhanced inference something model. So you need to think a lot, while in the BERT, it's fairly straightforward how to do that. That's like the power of BERT. And now I'll give you like a set of recommendations for training these models. First of all, what we found out is that training is okay for this like imbalanced data set. Training is fine, you can do that. But the problem is that if you don't have big validation data set, you actually don't know whether your hypothesis makes sense or not. So recommendation is to choose your hypothesis wisely and don't experiment like extensively. So think about the problem extensively before you apply some very nice recent research paper. Also, we fine-tune hyperparameters, but it rarely helps. So default ones that you find from the papers mostly work. And we did some optimization with Optuna for different tasks. And actually, it wasn't so beneficial. And also, it's more likely that you overfit to your small validation set. And also recommend, this is the paper from Jeremy Howard, as I said, that using any form of learning rate scheduler will be beneficial for training big models, because that way you can prevent for overfitting. Another technique that you need to take in mind, or don't take in mind, is like early stopping, because the idea of early stopping is I cannot train too long on the train set, so I will try to short the training time as to be small as possible, so I don't overfit, and at the same time I have like the highest score in the validation set. But the problem is that if you don't have a big validation data set, you will actually overfit to your validation set. So this technique doesn't work for like small data sets, and you can solve that using different techniques, because if you're using some learning rate schedulers, basically it adapts to your length of training. Like some of them adapt to the length of training. So they will allow you to train the model longer, so we don't need early stopping to train it as short as possible, but at the same time, it won't overfit to your validation data set. So the recommendation is don't use early stopping. And also it confuses a lot if you're doing that in default fashion, like cross-validation, because then if you like stop and one fault, you don't know how to do that when you retrain the model for your whole like training set. So don't do that in a cross-validation fashion. Also, I recommend to track your validation metrics frequently, because usually with the big models, and these are few-shot learners, you rarely need to sweep through your whole data set. because it's like you need a few examples just to reach the expected metric value, and then it's very flat and starts dropping, or like into some oscillation mode. So, and if you don't do that, you can have some misconception, because you might think that, okay, I have 2 big learning rates, so it needs to be lower, but it doesn't have to be lower, because then you can underfit a lot if you don't have good learning rate. So I just recommend not to report that every epoch, but for example, after some batches. And for example, NLP has a flag for that, or like PyTorch Lightning as well as a framework for training has this setting in a trainer object. And especially for BERT models, I recommend not to play with batch size very much. Just utilize your GPU to the fullest, because the power of BERT is like speed of training. LSTMs were better in our experiments, but they trained much longer. So you can just kind of monitor the resources for GPUs and see whether you use batch size that like maximizes your memory of GPU. And speaking of memory, buy at least 20 GB of your GPU, because like BERT base requires you 12 gigabytes for batch size equals to 4. So otherwise, we had, for example, buy some GPUs 11 gigabytes, and we like missing 1 gigabyte to like train with batch size equals to 4. So we can train with 3, but then it's hard to like reproduce fully all of the papers with BERT. And the last recommendation is that sometimes we added weight decay, but in the BERT architecture, you have normalization layers, and you need to just remember not to add that normalization layers, because they are like to propagate the gradient properly, and it will like make a lot of mess, and it will be hard to debug for you. Okay, so I will share also like one trick that we find useful training on the imbalanced dataset. As I said, the imbalanceness we defined was like roughly around like 4%. And this is a paper called Focal Loss, and it was from like dense object detection. So the whole idea is that you have like cross entropy. You have this this kind of smoothing term in the middle, like 1 minus p to the power of gamma. And what it does does 2 things. First of all, it downweights the easy examples. So if you have like an easy example and the unbalanced data set, which are like zeros in our case, it won't train further. So once it achieves like some sort of probability, like for example 0.6, then it's like stops training. Like it kind of misses. It behaves like this example didn't exist. So it's like it treated it as I trained that and I don't train any longer. So as I said, it has like second property that it actually allows you to train longer, because you won't overfit so quickly to your train set, because otherwise you would see like your loss decreasing very much. But actually this kind of gains in loss would be artificial, because it will be for like your zeros in the data set. And here you can like easily see actual gain and loss for your training. So other trick also reported in the paper is to add some prior knowledge to your layer. So if you know in advance that your problem is imbalanced and your labels will also come in an unbalanced way, then what you can do is to like by hand initialize the bias of your network. And for example, the argument for the logarithm here is like an inverse odds ratio from logistic regression. And basically you can think of as P as some sort of probability of the rare class. So if you know that you have some imbalanceness, you can put the P there and have a bias. So by default, at the beginning of the training, your model will predict like a default value. So it's like, which is like low probability instead of like 50-50. So yeah, so that's like a nice trick to add to training. And also when we experimented with that, we tried values much higher than 1, because in the paper, they recommended to use values from 0 to 1, but we actually had much gain if we tried values higher than 1. And for example, in the past, it was similar story with the learning rate, because it was believed that learning rate should be from the range 0 to 1. But there was like a paper from Leslie Smith about superconvergence, and basically it was an attempt to try networked with like crazy values of learning rate, like 3, 2, 5, and it worked. So do the same with focal loss. And we noticed hardly any improvement with the lower values. And also, okay, because I said weight, but in the equations I showed you, you can do the same trick, but with like weighted cross entropy or weighted focal loss. So this is the weight I'm referring to. And transferring the same weight from like regular weighted cross entropy really helped. So you need to experiment a bit with that. And this is what I told you, that it allows you to train models for longer. And because if you have like a very sparse data set, those positive examples, you can actually sweep through them multiple of times. So that's a nice trick that you can utilize in your like research. Okay, so I showed you that some imbalanced data set with the imbalance ratio roughly around like 4% can be trained with big models. Still, TF-IDF is a very strong benchmark for our case. But once we had a study with our client who came to us with a systematic review and said, okay, guys, I need your help, but I have only 3 included studies in the review. And then it becomes very tricky because with 3 examples, you really don't know, first of all, how to make the recall because you have 3 examples, and second of all, how to actually split that into training, validation, or test set, or maybe even in the cross-validation fashion. It's tricky. It's tricky. So we used unsupervised models for that. And here is one thing for maybe some of you don't know, that actually BERT doesn't work well in unsupervised fashion. So if you try to use that out of the box and just calculate some cosine distances or something, it just won't work because you need to pre-train that for your specific task. So one of the methods of pre-training that in a supervised way is like something called triplet loss. And the idea is that if we have all of our positive example in our data set, we want these examples to be close. And at the same time, we want our positive examples to be far away from our like negative examples, which is 0 in our data set. So that's the idea. And we can define a loss in such a way. So if we define it that way, we can know that if we minimize that, we know that DAP should be like very low and DAN should be very high because of the minus. And adding M, it's like a margin. So we define what should be like the distance between these 2 examples, like pairs of examples. So we define something called triplet loss. And fun thing is that we found a paper from 2020 from Kevin Musgrave and a group on Facebook. And basically they kind of compared the relative improvement over time with how different losses were produced. And on the gray bar, you can see what was the relative improvement that was reported by the authors of the papers, while on the green and the red, you can see the actual improvement while they reproduced. So as far as I remember, triplet loss was firstly defined in 2006, and it was like 14 years of work. People compared not apples to apples, but like using different architectures, and they assigned this improvement to different architectures, not to the loss itself. So go with triplet loss, and you can experiment with different losses, but triplet loss is like good enough for you for your experiment. That's what I'm trying to tell. So we collected data set for our task. We collected 36 systematic reviews. These are statistics. Our imbalance ratio is roughly around 2% this time. But it doesn't matter because we're not training in the regular like fine-tuning fashion. Totally, we have roughly around 2,000 included studies amongst all reviews. And the idea is that you can use all of those 2,000 examples to generate triplets. So generating triplets, for example, if the single systematic review has 10 included examples, then we can generate like all of the unique combination, which is like 45 triplets. And one thing worth mentioning is that for the triplet, we also need a negative examples. We cannot only work with positive examples because otherwise it will be like contrastive loss, not triplet loss. And these negative examples were sampled at random, But since they belong to one systematic review and like all the rows in the systematic reviews comes from a single search, they have something in common. So they are not like easy examples, they are sort of like semi-hard or semi-easy examples in our case. So that's worth mentioning, because in triplet laws, people usually try to find some kind of balance between like hard examples, easy examples, semi-hard examples, etc. So we have like semi-hard examples by default. So out of roughly 2,000 included studies, we managed to generate like 85 triplets for our training and validation, and now we can actually robustly estimate all of the things. We used a Ariander curve for the ROC curve, which measures separability between positive examples and negative examples. It's like one of the standard procedure as well for training such networks. And to mention in the paper that we didn't do well, but I will share it with you so you don't repeat our mistakes. First of all, you need to check the importance of the batch size. One paper from Kevin Musgrave, they report that batch size actually doesn't matter in their experiments, but actually there is a different paper called like CLR. One of the authors is like Tin King Chen or Jeffrey Hinton, and actually they reported that if you go with the like higher batch size values to like 128, it's very beneficial for learning, and also training for a longer time is very beneficial. So we need to check it by yourself. And the other thing that you need to remember is that later on, if you want to work with your model and you want to like set up some distances in a supervised fashion, you need to avoid something called coercive dimensionality, because in the high dimensionality, distances will be like very close. The points will be very close to each other. So setting up the distance threshold will be very hard. So in your network, you need to have some sort of like projection, like a regular fully connected layer on top of BERT to project that lower dimensionality. Usually people use like 128 dimensional vector. So we did some hyperparameter tuning, and it seems like triplet distance, which is the most important, was whether we should go with cosine distance or L2 distance. So it mattered the most. Triplet margin was this M from the equation. Pooling technique basically means that whether we should use the CLS vector from BERT or should we like use the mean vector. Weight decay is self-explanatory. This doesn't matter, so I won't explain them. Yeah, and a bit of dropout. But even though the Optuna, because it was tuned using Optuna, it's like the triplet distance is very high, the optimization history looks like follows. So we started from something around our Ariander curve equals to 84%, but we improved to like 86 something. So the gain is not significant, and we had like around 40 trials. So this is what I referred to. It's not like, it's not worth spending a lot of time on that. You can spend, you just can automatically do some Bayesian optimizations, but trying to do that by yourself is rarely a good idea. So once we train our model, we have some representations for our documents using BERT. So we now want to compare them in a ranking way. So what we did is we picked at least one included study, and then we were looking for distances to, like, we kind of sorted our rest of the list to this like one included study. And we did that multiple of times, sample multiple of times. This one included study sorted many times, and this is the chart we got. So this is purely unsupervised, like no training is involved. And the blue line is like other embeddings. The orange one is something called Spectre. They did something similar with triplet laws, but they trained the model on the citation network. So they just think that if the two articles cite each other, or like one cite the other one, then it should be close to each other. And if the citation is like far away in the network, then it's like not very close to your article. So they train embedding on that, and we compare it to them. And as I said, SciBERT used purely in the unsupervised way, because there are different BERT, like SciBERT, PubMed BERT, BioBERT. We just use SciBERT here, and regular TF-IDF. And our goal is to rank in such a way that we achieve the recall 95% or 100% as fast as possible. So this kind of dashed black line is some sort of like a finish line. And so for this particular systematic review, we win. For different, we actually lose. And my hypothesis is that the distribution of the training examples doesn't cover the systematic review for the dataset. Maybe they relate to a different domain. They speak about something different. So we failed on that example. A different example is also very interesting because, for example, Spectre starts very, very strongly at the beginning of the race. But then, since we are interested in the recall, they actually fail in the second part of the race because yeah. And even though TF-IDF still is a strong benchmark, we actually, and it beats us on 95% recall, we actually win on like 100. And in the same way, if we set up the finish line at recall equals to 100, so it's kind of the same. So more in a more in the scientific way, this is the results that we got in terms of WSS. So still TF-IDF is a good benchmark. Perhaps we overfit a bit to validation set. Perhaps we didn't. Maybe it's a different distribution of the articles. That's fine. If we set up the threshold differently, so we are interested in WSS to be 100%, then actually we win in this case. So we found a case where our embeddings might be useful. Okay, so now we can apply our embeddings, but I owe you some kind of explanation because until now, the training setting was kind of weird, if you think about that, because first of all, we had to have like 50% of data sets to even start training in supervised fashion. Then the second approach was that we only ranked the document. We didn't actually saved any work because we only ranked document. We never told people when they should stop screening. We only evaluated well how soon they are evaluating, how soon they get required recall. But we never told them that. We can only evaluate that after they are done with the whole work. So it's not very beneficial, but anyway, we find pseudo applications. First of all, the first setting works fine. If you have an existing systematic review and you want to update that review. Of course, you need a different validation because you need to validate over time since you're just updating the review, but you can actually update existing review. And the second application for the supervised fashion is that you can validate the existing systematic reviews. So you can do that in the following fashion. You split data set 50-50, you train model on the one half, you validate in the second half, but then you switch the false and you train again and check on the first half. And then you compare basically the predictions of your model to like your whole systematic review. Yeah, so we never told you when to stop. And basically the problem is how we can convert these distances or these predictions into binary label. And basically, if I need one slide, and I have one slide, don't do that. If you have a sparse validation set, we haven't found a way how to do it effectively because it kicked us into the asses that sometimes we try to estimate some threshold, to cut off threshold, and then we estimated WSS to be some value, and in reality, it wasn't the value that we expected. So it's very hard to estimate that on validation data set. The variability of the recall estimates varied very, very much. And also varied within and across systematic reviews. And it refers only to very imbalanced data sets. If you have more data, of course, you can have better estimate. You can, of course, say, okay, I will go with argmax, which is default thresholds, that's fine. But if you have the goal that we had, which is achieve required recall, then you won't achieve this recall. You can try different things. For example, you can try to embed this threshold estimation to your training procedure, and it's fine. But again, you want to get the same required recall for the shallow models, like based on TF-IDF, people use linear SVM because they don't give you probabilities. They give you like 1-0 out of the box. And for deep models, there is nice paper. I don't have time to tell more, but this is like SparMax, and it returns you like the sparse distribution from your model. For unsupervised models as well, we don't have a good recommendation. The only model I think I know, unparametric one, is like nearest neighbors, but for distances, it's not straightforward because if you have imbalanced data set, then you don't know how to estimate K, but still you need to estimate K. So we want to avoid estimation, but here we still need to do some estimation, and K equals to 1 doesn't make sense because it would mean that all our like included examples should be like very close to each other, which means that on the ranking curve I've shown you, it should be like all should be like vertical if they are like K, if K equals to 1 should work. So it doesn't work well. Yeah, so regardless of the problems we had on like very imbalanced data sets, and by very imbalanced, I mean like below like 1%, like very much below 1%, we managed to help some people using the models we had. So first of all, it was the systematic review referred to physical distancing and wearing masks for COVID, and they had roughly 20K documents to screen in 2 weeks. Now they have around 60K documents planned to screen for update. And you see the numbers I show you right now, like 20K, 60K, are like very different from the numbers I showed you in the systematic reviews previously. So now actually it makes sense to use some automation. Because if you have like 1,000 example, probably you don't need any automation. So there were like 40 people involved in the double screening process, and double screening process is the process that each study needs to be screened by 2 people. So what we did, we did the setting that I've explained earlier. Just we do that in the like, cross-validated way. So we trained the model on like one part, and we validated on the we trained on the one part, and we validated on the second part, which is like 50%, and then we switched and trained on the second part and validated on the first part. So that way we kind of identified missed studies. And we were able to do that because 40 people were involved in the screening process, meaning that the probability that 2 people with like low experience will see the same study is like higher with 40 people than with like 3 people. So we helped with that. It was like cited more than 1,000 times, and actually after the publication of the study, the guidance from WHO changed, so now we all need to wear masks. So that's the first case study. Second study is about update for anticoagulation for thermal prophylaxis with patients with COVID, and this was with collaboration with American Society of Hematology. They have roughly 50K documents to screen every month, and in the first update they had 100,000 documents to screen. In the second update, they had roughly 200,000 studies to screen. So we managed to achieve this kind of workload reduction significantly without compromising recall. But as I said here about WSS metric, it's kind of not easy to cheat, but if you have a lot of examples, it's kind of easy to have very big number in the workload savings, which is not the case if you have like 100 examples. So most of the reduction was from removing duplicates using our internal tool called Super Deduper, we call it, because since the data comes from different databases, they couldn't cope with duplicates removal by themselves. So we helped that a lot. And basically 50% of that is like removing duplicates for them. So I can briefly tell about this deduplication process, because since it was like 50% of workload reduction, it seems like a very significant step that some people miss in their applications. Of course, we used that our embeddings. So we compared our embeddings based on our, so we mapped each document to embedding, and we tried to look for a distance to some similar document. And it works because data comes from different sources. The problem is that people in the current market tools take into account only not only the title and abstract, like the text itself, but also like metadata, like authors, publications, years, etc. And what they do, they focus strictly on records removal. So what we propose is just, first of all, what do you need metadata if you just read title and abstract? So don't look at that while you're just doing the duplication. And first of all, don't remove duplicates, but aggregate duplicates. That's why you will keep your like metadata, because metadata mostly are used for full text retrieval. So based on that, we had like over like from 9 to 17% improvement over different deduplication market tools, which uses some authors, publication, different metadata. Second of all, you have to do that if you want to train the model anyway, because then you will have some data leakage, and this almost the same data point will be like leaked into your validation set. So it's like must-have step. And the duplication itself is like squared complexity. So people try to use some heuristics, and they sort by different heuristics like titles, authors, years. Like there's like a paper that people tried to figure out some heuristics. Yeah, so it's like half of the work is the duplication that you need to do for our test. I have one paper to explain also, which is very simple and cool trick how you can speed up this quadratic complexity. And basically, it's based on triangle inequality and a distance space in a metric space. So our goal is to, for each vector P, find all vectors Q who are close to P. So this is basically our N square. So for every data point, we want to see distance to every data point, so we can evaluate whether our distance from P to Q is lower than some tau. This is our goal. The triangle inequality is defined as follows. And if you do some math, you will see that basically it defines by introducing some data point R, you can define the lower bound for your distance PQ. This is like the lower equation. And to assume that your distance function is symmetric, you can do the same, assuming distance PQ is the same from distance QP. So we have this knowledge. So we have some estimate on the lower bound of distance from P to Q. And based on that, we can formulate the sufficient condition. Because if we know that our lower bound for distance, we have estimated from here, from our condition, is higher than tau, then we are sure that it will never be lower than tau. There's no way that if our lower bound is higher than tau, then it won't be our acceptance regions, which is like our distances lower than tau. So that's our like sufficient condition. And if it's true, then we know that we can reject candidates. And how to translate that into some algorithm, because we have this, it works, but we have some very mysterious variable called R. So what we can do is do some pre-computation. We can construct, sample, choose whatever, any vector R. Then we can calculate distance from our every Q in a data point to this kind of artificial R or some indifferent data point. And then we can sort our distances here like Q and R. And this is like our sorted list on the right, we have distances. So this is pre-computation we have to do. And now if you're doing search, we're just picking some data point, for example, C. We know its distance PQ to R. And then if we want to calculate and then we need to calculate this, our sufficient condition. So for example, if we calculate distance from C to A, we have this P to R, Q to R, and we know that this is lower. So if it's lower, then we actually don't know. But if you calculate from C to D, and we know that 0.6 minus 0.1 is 0.5, and it's actually larger than our defined tau, which is 0.2, we actually know that we can reject that, but we can also reject all of the data points before that point. And the same reasoning is for the data point B. So for example, if you want to calculate the distances from C to every other point, having this pre-computation, we only need to calculate this from C to A and from C to E, because then we don't know what's the distance between C to A and C to E. And the same reasoning is in different examples. Okay, so that was a trick how to use the duplication. So what we found out so far, we know that we can rank documents. We can train big models using some if we have like enough validation data set. But if you have like very imbalanced data set, there is like, we didn't find an answer what to do. So now we try to find the answer, what we can do about that. So first of all, you always might notice that every time we had to train model for each systematic review, because each systematic review has some information, some training signal, which is like a column with labels 1 of 0. We don't want to that because there is some randomness involved in training and it's some technical challenge to solve. So we want to avoid it. Second of all, we would like to work with these highly imbalanced systematic reviews where we have like 3, 4, 5 examples involved. And not only train, because train, we can do that, but actually know what we can expect from this model and actually save time. So we not only rank the documents, but only we have some estimate that we know that, for example, if we set a threshold like that, we'll achieve this suggested recall, not lower, not higher. And second of all, we would also to help not only in updating the systematic reviews, but also in creation of systematic reviews. So we want to help in creation of systematic reviews from scratch, where no prior training data is required. So different groups try to solve that problem that they just using active learning and they start to gather data as fast as possible, and then retrain model based on the answers, and then pick studies to like improve model. So these approaches work. We experimented briefly with them as well, so that's fine. And also we would like to have more explorative approach, because when we talk to people, they actually don't do the work that if you tell them read that and don't read that, they usually don't trust the model. If you rank the documents, then they don't trust that way. They actually work in batches. The users work in batches. They just want to pick some studies that are about rats and try to look for them, and maybe some other documents. And also we would like to see the knowledge gaps in the literature. So these are our objectives. So we try to solve the objectives. So first of all, we look at our process. So we know that before selecting the studies, we have search studies step and defining the questions and eligibility criteria. These are very important steps as we speak, because most of the irrelevant studies in the systematic reviews comes from not very precise Boolean search strategies that comes from different search engines. Second of all, the screening decisions, actually these eligibility criteria change over time. Sometimes people included case series and then they decided to exclude them because RCT studies were available. So for them, it's kind of like prediction what's in the database. They want to like predict what's in the database, and then they just want to create criteria in such a way that actually they can minimize the amount of work they have. And if you think about machine learning in general, what you do, you have binary label, you have unknown factors like a vector representation, and what you're trying to do is like decode the either representation or the factors from a training signal. The problem is that I find it impossible to do that with very sparse training signal, like with the imbalanced data set. And if you take a look at the process, actually people define the factors and the composition using inclusion criteria. So basically, this is something we have. Some people might tell that, okay, randomized study only I want, adults older than 6 years old with some stages of asthma. I want studies with 10 participants, or the participants should receive some drug in some dosage over some time. This is what people would like to query. So in other words, if we have like a space of all documents and we have all matching documents for our criteria, what we have is this yellow area. It's our training signal. And the problem is that it depends how the training signal was sampled, because if we have all our positive examples very similar, then we could barely generalize from that. And we had this like special case when our client gave us a training data set and we had all positive examples which were very similar. So we did all this cross-validation, regular training, and we ended up with like very good prediction, but we ended up with very good prediction because all of the positive examples were very similar, but in practice, it didn't generalize well. It didn't do well on the test set. So yeah. So basically, it is the robustness of our estimates is kind of bounded to what's in the data, what they achieved to find in dataset. And we'll never generalize beyond areas that we have data points here. And also some imbalanceness comes from the fact that just, for example, some diseases are rare, and then if we try to combine them with using like a chain rule probabilistically, then it's like a composition of different factors. If you have like a rare disease compared with the rare study, compared with like the rare group of people, then it's likely we can help using this standard training approach. And also in this ranking curve, we had these kind of tails. If you had this, remember this race, we had to achieve recall 95%. Then actually the biggest issue was to catch this kind of this tail of this ranking curve. And these actually are indirect evidences, and people sometimes have some backup decisions that didn't follow initial criteria what they want, but they just included that just in case maybe the full text will contain the stuff we want. So our solution is to, instead of trying to build representation vector based on TF-IDF, trying to decode that using some embedding string of triplet laws, we just think that our representation should be meaningful for people. So for example, instead of training the model with the right column, which is binary decision, which has imbalance ratio 0.2 for such example we have, and number of samples is 63, we can think about study about what people are looking. And for example, they want to look for study type. They want to know for condition of patients that were into the study. They want to know what drug they kind of received or what they compare this drug to. So this is like an example from one systematic review that if we split that binary decision into like criteria we have, then this imbalance ratio is much higher, and we actually train the model for each of the columns separately. And then we can also estimate the threshold for each column separately. So, so this is our approach. It's a bit longer approach, but it's very promising. And yeah, that's our solution to that problem of imbalancedness. So thank you very much for your attention. And if you have any questions, please ask. If you would like to work with us, also we can text us on LinkedIn. So thank you very much.
Thank you, Mateusz. That was really packed with knowledge and practical stuff. I also realized one of the problems we work on is it could be framed as an imbalanced classification of text. So we will definitely take a closer look at your work. I have one question, and you can also ask questions in the QA panel or in chat, and we will try to answer them. So my question is, well, with the numbers you've shown of tens of thousands of papers to screen, that really shows the scale of the work. But in real world applications, what is the recall you're trying to achieve? Is it like 95% or it's not really defined in such a systematic?
It's not defined really strictly. This 95% comes from like one specific study, but reality is reality. So we had one client who was, let's say, he didn't have enough resources, also he was just enough with maximizing WSS. So we ended up with like 83, for example, % of recall. And since he doesn't have resource to do that manually, he's happy with that, because having like recall 83%, he can reduce his workload by like 70%, for example, and it's still good for him for the update, because we need to remember that there's a difference between update and creation. Systematic reviews mostly are used for guidelines for human health, so this unbiasedness and this recall is very important. But for updates, it's not like very strictly regulated in terms of the law, etc. So updates like living reviews are like not the application that we can actually lower the recall. And for example, our scientific chief scientific officer says that specializes in systematic reviews. He claims that from his experience is from 80 to 90 in real life. But it's just like his opinion, so we probably would need to do a systematic review on that.
I also had a realization when you showed these graphs with comparison of how the curves go up with the number of documents reviewed, that it's really a different problem than information retrieval, because it's not enough to just show the top 20. Yeah,
yes.
It's not enough to just show the top 20 results which fill the first page, and then you don't care. It really, you want to catch almost all the documents as quickly as possible. Yeah,
some metrics like NDCG won't work here.
Yeah, that was supposed to. I was going to ask about NDCG, and that's. But after these plots, I realized it's really a different problem. So we have a question from Grzegorz. Have you tried rule-based methods, such as based on regular expressions? And how could this compare to deep learning?
We haven't, but I know that there are studies that are actually using rule-based methods, and I know that they help. For example, there is like a benchmark called EBM NLP, and there is like a task to predict the intervention from the study. So intervention is, for example, a drug that people take, and they managed to improve that using some like regex expression. As well, I know some paper for different purpose, but related, just for the update, that a person tried to classify whether the systematic review needs an update. So he used some kind of regex trying to from some regex extract the simple rule, like number of population n equals to, and then he extract the number. And based on that, he extracted some of the numbers, like some features from the review. And based on that rule expression, like regular expressions, he managed to actually predict with very simple method whether the systematic review requires the update. So we didn't do that, but some people for slightly different purposes uses that. Did I answer the question?
Okay, that's probably a question for Grzegorz. If you want to follow up, just please, Grzegorz, if you want to follow up to this answer, just ask another question. And okay, so yeah. Do we have more questions? Okay. We have another one from Grzegorz. Grzegorz, you can use your mic now. But the question is, where do you prefer to use batch norm, before or after activation?
To be honest, I don't know. I don't have any preference. We use layer normalization instead of batch norm. But since we fine tuning, it's like layer normalization involved in BERT. So I don't know whether people use batch norm anymore with layer normalizations. Maybe you know.
Okay. Do we have any more questions? Okay, I think we have no questions, no more questions. So Mateusz, thanks again. This will be available. This recording will be available, and we also welcome you all to come to our further open seminars. We plan more. So thank you, and see you in the future.
Okay.
I hope.
Okay. Thank you very much. Thank you.